In order to illustrate convergence, we're going to look at a very simple example. So I'm going to have two lines, two graphs plotted here. So one of them is going to be y equals x, so the line that's kind of going at a 45-degree angle. So this is y equals x, and then the other line is going to be some function that we're interested in. So I'm going to just call it f of x. So y equals f of x. All right, so what we're interested in is finding the intersection point, the point where the x-axis and the y value, the x value and the y value are kind of identical. And in order to do this, we're going to start with an initial guess. So we're going to say that, well, what about for example, this value? What if this particular value, let's call it actually x0, what if this value happens to be the right value? And what we do then is we draw a line from this point to the point on the actual graph, so we get to see whether our result is in fact correct. So we end up here and we see that obviously the x and y coordinates are not the same. The y coordinate is much greater than the x. So what we do then is we draw a horizontal line from this point towards the point y equals x. And so we draw a kind of horizontal line in this direction, and we end up somewhere here. Okay, so now that we end up on this point, and we can call it x1, by the way. So this particular point is going to be called x1. So at this particular point, what we do is we once again draw a vertical line towards the curve. So we draw a vertical line towards y equals f of x. We end up at this particular point. And so what we do afterwards is we continue the process. So we go left back to the line, we go back up to this line, to the right, to the right, to the right, and eventually we converge to the point that we're actually interested in. So this is a simple illustration of convergence. Effectively, we converge to the point that we were actually looking for. However, this approach does not always work. In some cases, you might have the same kind of setup, but it simply will not work. So let's take a look at an example of that, a different kind of plot. So once again, we're going to have y equals x going like this, y equals x, and then we're going to have some function that goes like this. So we're going to have this function y equals f of x. And now let's suppose that we once again adopt this approach of picking some point x0. And you'll notice that in actual fact what's happening here is if we want to find out the point of an intersection, which is actually somewhere at the origin, we're not going to get it. Because what happens as we pick some initial value x0, we go up towards the function, we go right towards the line y equals x, then we go orthogonally once again towards the function, we go right towards y equals x, we go up to well, almost infinity, and we're never going to get the result, which is that they intersect somewhere near the origin. So in this case, what we're looking at is divergence. We're looking at a situation where there is no convergence, and that's what's called divergence. So this method actually converges if in the neighborhood of the intersection point, the derivative has an absolute value that's smaller than 1. So let's write this down and let's take a look at an example of that. So we have this requirement that for the function f of x, we're going to converge if the derivative of this function has an absolute value less than 1. If this is the case, then it's going to converge. So for example, let's suppose that we have f of x being equal to 2 divided by e to the x plus 1. So the first derivative of that, f prime of x, is equal to minus 2 e to the x divided by e to the x plus 1 squared. Okay, so let's draw this. Let's have the y and x axes, so the line going like this a bit, and let's suppose that y equals x is still what we're interested in. So we're interested in this particular point, and we might have different guesses as to our initial guess. So we might have x being equal to 1 and x being equal to 3. These are the two guesses. So let's take a look at the first derivative at x equals 1 and at x equals 3. So the first derivative at x being equal to 1 is equal to minus 2e divided by e plus 1 squared. So that would be about minus 0.39. So that's certainly less than 1 in magnitude. On the other hand, the first derivative at x equals 3, which is equal to minus 2e cubed divided by e cubed plus 1 squared, is also within that limit. It's actually much smaller. It's about minus 0.09. So essentially, in this case, what's happening is we are satisfying this condition. We are satisfying the condition that the first derivative is smaller than 1. So the values that are being provided and the approach that we take will actually be convergent and will actually find our intersection point. And of course, we can draw the diagram with any of the starting values. So I'm going to choose a different color. If I start at the value of 1, I'm going to get here, then here, then here, then here. And you can see that it eventually gets right to the point where we need to be. And similarly, if I start outside, if I start at 3, what will happen is I go up here, then I go left here, and then it's the same as the green path, and we're going to converge.